welcome to this product demonstration. My name is Gerhard Steiner, together with my colleague Frank Tettrich, who is still there in the off.
Good morning.
We are going to present you the setup of a Grimm SMPS+C system, show you the unboxing, show you the individual components, describe them, and then also will give you a tour through the software, what possibilities we have using the Grimm Nano software. So first of all, a look at the box that you typically get when you purchase a Grimm SMPS+C system. It's delivered in this pelly case, where everything is neatly packed, so it's also for later on use quite useful to use that box when you want to ship it to your destination of desire, to your measurement site, to your field campaign. So it has got several layers. On the top layer there is some accessories, there is a some tubing, all the electrical connections. There is also a kit with spare parts and some basic tools to do some maintenance on your instruments. This is the first layer. Thanks, Frank. On the second layer, I hope you see that in more detail. There you can already see the main instrument, the 5416 CPC. More to that in a minute. And there's also a first accessory to take out a base plate where we can put all the other instruments on top of it later on. So removing that layer, that also includes a universal power plug, typically. So there you can see more instruments in there. The CPC, there is also a compartment for the measurement computer, typically. There is a compartment for the differential mobility analyzer, another one for drain and butanol fill bottles. But first we need the main instrument, the CPC model 5416. This is the one, and this is more or less the top range model of CPCs we have at Grimm. There is actually another one called the 5417. It's a new model, the brand new model. This version here has got an integrated DMA voltage controller, so you can hook up a DMA onto to this instrument. It has got an integrated sheath air supply, supplying 3 liters a minute for the sheath flow. This model has got a sample inlet flow rate of 0.3 liters a minute. The 5417 is the more advanced version of this one here. We are presenting it in course of the so-called SMPS setup. If you want to know more about that, you are cordially welcome to watch my video on the SMPS setup, where the 5417 CPC is part of it. It's also featured today in the aerosol measurement technique session, 2:30, I believe, where the setup and all the features of the SMPS will be discussed. The 5417 has, in addition to the 3 liters a minute sheath flow supply, another flow possibility of 10 liters per minute, and also a second option for the inlet flow rate of 0.6 liters a minute. All those flows are controlled by temperature stabilized critical orifices, and can be also set in the user software. So the 5416 CPC on the front, it's quite a clean setup of the whole instrument. On the front there are a couple of LED lights, LEDs, indicating the status and the operation of the instrument. So there is one LED showing if the heater of the critical orifices is on or off. Then the second one, if the sheath flow is switched on. Then there is a status LED showing if the DMA works correctly or is correctly hooked up to the instrument. Then an LED for power, another one if the temperature of the CPCs, if the set points of the temperatures are met already or not. So this indicates if it's already in operating condition. Then there is a general status LED that indicates if some of the parameters are not yet met or are on their nominal values. And the last one shows the status of the liquid level. So this indicates if enough butanol is still in the saturator wick. So this is the front panel. On the back side, there are all the all the connections that's needed for operation. Most important for the CPC functionalities is here on top the liquid inlet port. This typical butanol fill bottle connectors. Then there is a port for connecting the DMA. Most importantly mentioned here is that the high voltage power supply for the DMA is not included in this instrument, but it's included in the DMA itself. So here, basically, just controlling voltages, setting the DMA voltages are connected. Then there is a USB port for connecting the instrument to a computer. Then there is a flash drive port to apply future firmware updates, but this can also be used to save data online on a flash drive stick. Then there is the possibility to hook up a specific metrological sensor, or actually there are a couple of different ones that can be used in addition to the data readings of the instrument. Then there is the here called condensate outlet. So this is the drain outlet of the CPC. Little bit more on that in a minute, and also an exhaust port where the instrument has the exhaust where particle-free but still butanol saturated air is leaving the instrument. Of course, it has got a main switch and a power cord connector, and so these are the typical features of the CPC. The condensate outlet, maybe one word more to that. So one thing that's quite special or typical for Grimm CPCs for many years already is that there is a condensate, a micro pump drawing off any excess condensate condensed liquid that's draining off the condenser, and this is drawn out of the instrument into a specific drain bottle here. On the top of the instrument there is the unit that's important for operating it together with the DMA. So here we have basically two ports. This is a sheath air outlet port and an excess air inlet port, and those ports are connected to a DMA, to the DMA sheath air tank, and the critical orifices that, as I said, are temperature stabilized and maintain this well-defined and well-controlled volume flow rate. So what we do when maybe one point more is maybe one of the most important ports of the instrument at all is the inlet port, the sample inlet port. It's here located on the left-hand side of the instrument. Something that's really unique, at least to my knowledge, is this key operation of the sample inlet. So what we have here is the so-called saturator key. It operates a mechanism that physically shuts off the CPC saturator from the condenser and the following optics. So this is a kind of a safety feature that when you handle it or have to move or transport the instrument, you do not necessarily need to drain or to dry the instrument completely. What you just have to do is to turn that key so the shutter closes and no butanol at all can physically enter the condenser, or which is most important, can enter the optics and to damage any of the optics in there. So we will take that out one here and exchange it by a simple inlet tube. So what we then typically mount first is butanol fill and the excess and the butanol fill and the condensate drain bottle. So this is the butanol fill bottle. What we have here at Grimm are those magnetic snap-on holders, and the butanol fill bottle is simply plugged in at this point. The head cap of the butanol bottle is also provided with a tube that we can later on, which needs of course to be opened so that the butanol can be drawn out of this reservoir into the saturator. And we can later on connect this also to the exhaust port, that there is no unnecessary butanol smell in the room. So second is the condensate bottle, the drain bottle, snapped on the bottom and also plugged in. What else? Of course, power here on the bottom. Another one is what we typically use is a USB cable to connect it with the controlling and measuring computer. Something I may have missed in the beginning was that there is also an optional serial port RS232 port, which you could also use for connecting it to a computer if you like. Then what we typically use is those 8mm polyurethane or polycarbonate tubing for connecting the CPC to the DMA. So sheath air outlet here on top, we use yellow for that. Excess air outlet on the bottom, this would be the black one. So now I'm going to turn the instrument around and ask my colleague for the DMA. This is the long column DMA, Vienna type DMA of Grimm. At Grimm we have 3 different models in the instrument portfolio. So this is the long one, the L DMA. There is another one, the M, it's the middle length size, and as you could imagine, there is also one called S DMA. It's the smallest one. In combination with the 5416, it's quite, well, maybe just feasible to use middle or long DMAs. The long DMA has a channel length of 350 millimeters, and if it's operated with the sheath flow that can be supplied by the 5416 CPC, which is 3 liters a minute. It has got a size range from 10 to roughly 1,100 nanometers, so 1.1 micron. This middle length size has got a length of 88 millimeters, and if it's used at that flow rates, it has a size range between 5 and 350 millimeters. This is the in this version the so-called UDMA. So there is a conversion kit available where you can convert this long column DMA into this middle-sized DMA, and if you like, you could also convert it in the so-called SDMA. The SDMA has a channel length of 15 millimeters. It's way more feasible to operate it at somehow enlarged sheath flow rates. So this was one of the reasons why we developed the 5417 DMA CPC, excuse me, where we have a sheath flow of 10 liters a minute, and the SDMA at 10 liters a minute has a size range between 1.1 and 55.7 nanometers. If you want to know more about that, again, you are welcome to watch my video on the SMPS system in course of the ESC, online ESC here in Aachen. So this is the specs. This is the setup of the DMA. When you get it, there are some dust protection caps on the sheath air inlet and on the excess air outlet. The excess air outlet is included in what we call the DMA base. There is already one filter included to filter the excess air and to save the internal sheath air pump not to be contaminated with dirt too much. This is the sample air outlet, and we have these marks here on the base plate that we can nicely place the DMA here next to the CPC and have them well positioned to each other, and gives the nice compact setup of the instruments. So the sheath air inlet is here on top of it, the excess air outlet on the bottom. Another special feature of the Grimm DMAs is that we have the possibility to attach a aerosol neutralizer directly to the DMA. So in this case, this is an americium 241 source, and if you are if you connect it directly to the DMA, there are much less strict regulations active to transport it and to handle it, and also it's also a safety feature that it's bolted to the instrumentation and therefore cannot be get loose or just be taken by a colleague because he or she will need it in some other experiment. So it's nicely stored there also. There are some other there are not only the americium source available at Grimm, but there is also a soft X-ray source, then a nickel 63 source, and the so-called ADBD, the annular dielectric barrier discharge source. All of them are bipolar sources establishing a Fuchs-Boltzmann charge equilibrium. The DMA is also connected directly to the instrument, and here on top of the instrument of the DMA is the aerosol inlet port. The inlet contains already an impactor. So for the long column DMA, We have various impactor plates available. With this one, the cutoff is in the range of 1,200 nanometers, so ensuring an upper size limit of the size distribution you are measuring, and therefore ensuring that the data inversion algorithm works correctly. So this is, as I believe, the basic setup of a Grimm SMPS. So we could now connect the aerosol source in. We could now connect our aerosol source, the sample inlet to the instrument, start the software, and start the measurement. I will show you some of the features of the software just in a minute. Just to mention, this is what we also call the desktop lab version of the instrumentation. All of that is also available in a 19-inch rack version that can be easily mounted in measurement stations, in containers, in 19-inch rack supports to be operated in the field. So this was the first tour of all the instrumentation. May I ask, are there any questions from the audience about this setup, about the instrument? It appears not. In this case, I would like to go behind the screen and share with you my screen of the Grimm Universal Nano software. Various operation modes. In short, so the possibilities are scanning, stepping, single channel, and counter. Scanning, the fastest possibility to scan a whole size distribution. Stepping is to do it more slowly and do it in a more customized way of your specified size limits you would desire. Single channel is to generate monodispersed aerosol out, cutting out a specified monodispersed diameter out of a broad size distribution to use it, for example, as a calibration aerosol to calibrate some other instrument in your setup. And obviously, as I said in the beginning, it could also be just used as a counter where no DMA is connected to the instrument to just record the total number concentration of aerosol. So in this case, I would like to use it as a scanning mode because it gives us the broadest variability of settings. Here you could also enter a location code and also enter a dilution ratio if there is some diluter, for example, used at your inlet. This is not the case at the moment. In the communications tab, you would here connect the COM port you are typically using. Something you want to use is the time of the measurement computer. Another option, if you use it for long-term measurements, is to create one new file per day. Then there is the option to combine it as a wide range system. I believe tomorrow there will be a demonstration of the 11D optical aerosol spectrometer, and this instrument can be combined with the SMPS+C system to have a combined wide range aerosol spectrometer that can then access the size range from let's say 5 nanometers up to 35 microns and give you an overall size distribution of that. Then you could also connect it with a data logger where the data is then stored on a previously specified web server. Then there are settings for the carrier gas, the gas type you are using, the pressure and the temperature. Most often this will not be of an issue. But for example, if you use it at high altitude measurement stations, let's say Jungfraujoch, let's say Sondlik in Austria or wherever, where you have a decreased pressure, this pressure will then also, of course, affect your mobility measurement of the DMA and therefore affect the whole size distribution calculation, and you could account for this lower pressure already here in the settings tab. Of course, all of that can be used or can be set also in post-processing, so nothing is lost when you use the wrong pressure here. All the raw data is recorded and can be recalculated and re-evaluated at any point you desire. So fourth tab is the used DMA. Here you have the possibilities to choose between the LDMA, the long column DMA with 350 millimeters channel length. There is this box Vienna checked, because in former days there were also different types of DMAs in the Grimm portfolio, but since I believe 10 years it's the Vienna type DMA or even longer. The charger type here is called standard. Then the DMA type you can choose between one of those three lengths. Let's stay with the LDMA. Then there is the sheath air set to 3 liters a minute and the sample air to 0.3 liters a minute. In this case, you cannot change. You cannot choose any other option here, because the software recognizes that this specific model, the 5416, is connected, that only is able to give you a sheath flow rate of 3 liters and a sample flow rate of 0.3 liters a minute. It would be different, for example, in the new version, the 5417. There you can choose between 3 and 10 and 0.3 and 0.6. Also, you may be aware that there is also a possibility of the SMPS+C system. So it's an SMPS combined with an electrometer. There we are using another sheath flow supply unit called the DMA controller, and that one can also provide a broader variety of different flow rates, up to 20 liters per minute. So this is not the case here. So with 3 liters per minute sheath flow, it has got a range between 10.25 and 1090.21 nanometer. Then there is a tab for the specified for especially for the counter or single channel mode. There you could specify the sample interval. So 1 second is typically used as a CPC. Again, here sample interval FCE. That would be used if you use an electrometer as a detector. Here diameter single channel. Here you would set the diameter of your interest that should be classified in a single channel mode of the DMA. Now everything is grayed out because we are using the scanning mode. Also, the stepping mode is grayed out. There is a standard setting of the stepping mode suggesting 54 channels starting at 10.23 nanometers going up to 1090. You can customize that to almost any values of your desire, if that's important for your application. Then the scanning mode. The default settings tell me here it's scanning from 20 to 100 nanometers. This is not the full range. If I type in here, for example, 10, it will set it to the minimum diameter that's possible, so that's 10.25. And if I set here the maximum to 1200, it will automatically set it to the maximum diameter, which is 1090. Then there is this X and P value. So X would mean that in this voltage ramp, there are 200 specified voltage points that the software sets, and P would be the duration each voltage, each set voltage is kept. The voltage is kept for that duration. There are some wait times between up and down scans. So typically the system starts with a down scan starting at high voltage, which would be 10,000 volts, by the way, scanning down to the minimum voltage of 5 volts, waits for 20 seconds, and immediately starts after the scan time with an upscan. TC would be the time that the system averages over the counts received by the detector, and then there is a TD additional plumbing time that accounts for the tube length between DMA and the detector. In our typical setup, this additional plumbing time is 0, but by whatever reason you may use some different tubing, some other length of tubing that will cause here an additional plumbing time that can be accounted for in this box here. Then number 8 of the tab is settings that you can make for the diffusional losses. What we have determined in our laboratory tests were effective length of the DMA and the typical inlet of the americium 241 source. So when we apply a laminar diffusion deposition model to typically recorded DMA penetrations, we can calculate an effective length of the DMA, which would be here in the case of the LDMA a length of 3.5 meters. In addition to that, we have an effective length of the inlet using this americium source of 38 centimeters. This effect, especially the effective length of your inlet, may vary because you may use some different neutralizer, you may have some different kind of inlet, and there you can decide on yourself which effective length of the inlet would be appropriate for your setup. And last but not least, there is a tab showing all the settings you just have made. It sums up all the settings the software will send to the CPC, and when we press now OK, which I will not do now because the CPC is not connected to this computer, all the settings would be sent to the CPC. The CPC would be set into its measurement conditions, and you could start the measurements then. So this was a tour through setting up the. This was a tour. I will go back to the front. This was a tour through unboxing an SMPS+C system from Grimm. We did set it up. I hope I was able to show you the individual components in detail and explain what those, how those instruments combine with each other and how we typically set it up. I did also show you a tour through the possible settings of the Nano software, and if you have any questions on that, I would be happy to take your questions. So, if there are no questions, or maybe other questions in the chat, maybe not. If there are no questions at the moment, you are welcome to contact us at any time during the online EAC in the chat box of our online booth. Again, today is a discussion session on this PSMPS setup, 2:30. If you're interested in that, maybe we will meet each other there. So thanks for watching, and goodbye.